Inverse functions is our next topic. You may recall last year we touched on inverse functions way back in term 1 when we were looking at functions, and we just briefly talked about what inverse functions were, what have you. So to start off with, let's just recap that idea. We said, well, we know y equals function x is a function. We know the rules for that. So for every x in a domain, there's a maximum of one y value. Satisfies the vertical line test, that sort of thing. Now, if we swap the x and y's around, we're going to get a different, relation at this stage. We still need to confirm whether or not it's a function. So swap the x and the y's around, we'll get some new relation, which will be very similar. So for instance, if I started with y equals x cubed plus x, swap them around, I get x equals y cubed plus y. Okay. Now, you then look at that new relation, and if it still satisfies the rule for a function, so in that new one, every x value in the domain there's a maximum of one y value. If it satisfies it, then we don't just call it the relation, that is the inverse function, because it is a function. So you have to start with a function, and you have to finish with a function when you swap. And the symbol is the -1 there. So don't make the mistake of thinking it means the function or the reciprocal of the function. It doesn't mean to the power of -1. That's the symbol for the inverse function. If you were to draw both of them on the same graph, then you would see symmetry around y equals x. So we reflect in y equals x. I guess that makes sense because you're swapping the x and the y's around. So, okay. What that therefore means is if the point AB is on the original function, then the point BA should be on the new one, the inverse. And the domain of the original one would become the range of the inverse, and the range of the original one becomes the domain of the inverse. So everything swaps around. So how do we test then? Okay. Well, again, we could use a line test. If we used a vertical line test to see if it is a function, we can use a horizontal line test, because we're swapping the x and the y's around, to see whether it has an inverse function. So let's have a look at our parabola. Y equals x squared. Well, no. It cuts twice when I draw a horizontal line. So it doesn't have an inverse function, it would simply have an inverse relation. Still be a relationship, but it's not a function. Y equals x cubed. Oh, look at that beautiful y equals x cubed. Trust me, that is a horizontal point of inflection. Use your imaginations. But it doesn't matter where I draw that horizontal line, it cuts it only once. So it will have an inverse function. So that one's good. When you think about it, most functions won't have, because most functions turn and have points and so on. So unless it's continually increasing or continually decreasing, it's not going to have an inverse function. The other way of doing it, of course, you could do it with algebra. So actually swap the x and the y's around and try and make y the subject. And if what you end up with is unique, then okay, it's an inverse function. So back to our parabola, if I swap the x and the y's around, I get x equals y squared. If I make y the subject, I get y equals plus or minus. It's not unique. There's two possible things it could be. It could be plus, it could be minus. So no good. Whereas with our cubic, x equals y cubed, make y the subject, and whilst we're just dealing with real numbers here, of course, y equals cube root of x. There is only one cube root of x in real numbers. So yes, that one is unique. So visually, obviously, is the quickest and the easiest, but if you don't know what the picture looks like, then play with the algebra and see whether you can come up with something unique. All right, so if the inverse relation, this is a mouthful, if the inverse relation of the function is a function, in other words, it has an inverse function, then they should cancel out, because inverses cancel each other out. Just like if you multiply then divide, you get back to where you started from. It's the same with every function. So if I substitute the function into the inverse function, I should just end up with x. They should cancel each other out. That's why when we're dealing with exponentials and we want to solve it, we log both sides, because we want to do the inverse. And the reverse should happen as well. If I substitute the inverse into the actual function, they should cancel each other out. And I'm left with x. Let's do an example of that. That's a hyperbola in case you don't recognise it. 2x plus 1 on 3 minus 2x. Bit of shifting happening, but it's our standard rectangular hyperbola moved around a bit. Let's work out the inverse. So I'll swap the x and the y's around, and I want to make y the subject of all this. All right. Quite a bit of algebra there, but I get it. So y is 3x minus 1 on 2x plus 2. Now comes the fun bit. I'm going to substitute the original function into that inverse function. There it is in all its glory. Fortunately, the denominators are the same in those fractions, so I can multiply everything by 3 minus 2x, play around with it, and sure enough, we end up with x. So that works. But just to prove it works both ways, now let's substitute the inverse function into the original function. And again, yes, we end up with x. Well, as I said, most functions won't have inverses. So in order to create inverses, we have to restrict the domain. And then we say, well, over this domain, it will have an inverse. You want to try and capture as much of the range as you possibly can when you restrict the domain. So you want to get a good piece of the curve. So y equals x cubed isn't going to be a problem because we know it has an inverse. So let's again draw up that beautiful, there it is, y equals x cubed, lovely curve. We know the domain of that curve is all real x and the range is all real y. In hindsight, I'm thinking this wasn't a good example. We're going to invert it. So now we have y equals x to the power of a third. Look what happens to the domain and range. They swap. So now because the range was all real y, so now the domain's all real x, and the domain was all real. Yeah, as I say, in hindsight, not a great example there, but trust me, they have swapped. I haven't just written down the same thing. They have actually swapped. If I was to draw it, there's the line y equals x. Ooh, and then we'd have our reflection in the line y equals x. All right, let's do a better one. Let's do one we're familiar with. Y equals e to the power of x, our exponential. There's our basic exponential, e to the power of x. The domain's all real x. The range is y is greater than 0. Okay, we know to undo the exponential, we log both sides. So the inverse of that is y equals the log of x. And the domain is x is greater than 0. So now we can see, the range has turned into the domain. And the range is all real y. The domain has turned into the range. And if we were to draw it, which I am going to do, of course, there it is, y equals log x. They have no points of intersection, those two graphs. They never meet. Well, okay, let's do one where we have to restrict the domain. We said y equals x squared doesn't work. So put it in our parabola. There it is. And we go, oh, well, the domain's all real x. Oh, yes. Range is y is greater than or equal to 0. Fantastic. Oh, hang on a sec. Fails the horizontal line test. Hasn't got an inverse. So I'm going to have to restrict the domain. I want to get a piece of that parabola to get as much of the range as possible. And I guess I've got two options. I could go x is greater than or equal to 0. That'll get the complete range. And if I just look at that piece, it'll satisfy the horizontal line test. Or I could go x is less than or equal to 0. We tend to go with the positives. So I'm going to go x is greater than or equal to 0. So the range stays the same. We haven't affected the range. So when we swap them over, y equals mine will be the positive square root of x, of course, I've gone for. The domain and the range, trust me, they have swapped over. And if I was to draw it, well, it's just the top half of the parabola there. We can see the reflection for y equals x to the power of a half. Let's have a look at an HSC question. So they gave us e to the minus x squared. They've told us it has 2 points of inflection, in case you couldn't tell. They want us to find the x coordinates. So, okay, we know possible inflection points are going to occur. Second derivative equals 0. Well, there's my first derivative. Differentiate again, I've got my second derivative. So I want to solve that as equal to 0. Now in this case, I've got the answers x equals plus or minus 1 on root 2. I do not have to go and confirm that these are inflection points, because they have told me it has 2 points of inflection. And I've found 2 possibilities. Well, because they've told me there's 2, then I must have found both of them. Now, if I'd come up with 3 solutions, okay, then I would have to go and check and see which ones are the inflection points. Explain why the domain must be restricted if it is to have an inverse function. I know you love these questions where you have to explain yourself. Let them know you know what you're talking about. And I guess we'll basically say, well, I got rather technical there. I suppose you could just say, oh, well, it fails the horizontal line test. That pretty much is it. But I've gone technical. In order to have an inverse function, there must exist a one-to-one relationship. You like that one? One-to-one. So for every x value, there's only one y value. And so, all right. But as I say, I mean, you probably could have just said, oh, well, it fails the horizontal line test, so therefore, you know. Let's find the formula. Fancy word for equation, I guess. And we're going to restrict it. They've told us to restrict it to x is greater than or equal to 0. Hey, swap the x and the y's round. We now want to make y the subject. Bit of work to do there. So minus y squared is log x. Y squared then becomes minus log x. I brought the negative in to make it the log of 1 on x. Now I'll find the square root of both sides. At this stage I've got plus or minus the square root of the log of 1 on x. Now, the domain of the original becomes the range of the inverse. So therefore, I only want to get answers that are positive. So it must be the positive square root I want for this one. So there's my inverse function, given the restriction on the domain. State the domain. Well, the range of the original function would become the domain of the inverse. And you can look back on the graph and you would notice that the range of the original one was between 0 and 1, but not including 0, because that was an asymptote. So therefore, that becomes the domain of my new one. And sketch it. I think you'll enjoy my sketch. Look at that, how good is that? Okay, so that's all for today. Just a quick recap on what inverse functions are.